Hello and welcome to my talk on safe control synthesis by input-constrained control variable functions. My name is Devansh Agrawal, and my advisor is Dimitra, Panagou. Here's the basic outline of the talk. We're going to be introducing the background, the problem statement, and then I'll be motivating the problem and demonstrating how we approach this solution using adaptive cruise control. Next, I'll show you a formal construction that works for any system, and finally, I'll show you simulation results, in particular with a case study of autonomous rendezvous with the International Space Station. So the problem that we're trying to tackle is safety critical controls. We're trying to find control actions that ensure the safety of a robotic or dynamic system. In particular, let's say our dynamics are given by some control affine system. So x dot equals f of x plus g of x times u, where u is in some bounded subset of Rn. We're given a safe set defined in terms of the superlevel set of some h function, where now this defines the subset of the domain which is safe. And the question that we're trying to answer is what set of control inputs u will ensure that the system remains safe. We're looking for some sort of feedback control law. One approach that has been developed is that of control variable functions. Suppose you have some class K function alpha, and if you can show that for all x in the safe set, then there exists a u such that h dot is greater than or equal to negative alpha h, then we say that h is a control variable function for s. And the key result is that if h is a control variable function for s, then any Lipschitz continuous control pi will ensure that s is forward invariant, provided it satisfies h dot is greater than or equal to negative alpha h. As you just saw, that we've got a range of flexibility over alpha, but the key idea is that we upper bound the trajectories of h of x of t, and therefore, since we lower bound, the trajectories of h of x of t by some non-negative function h, and since it's lower bounded, we know that the system will never exit the safe set. However, if you cannot show this condition that there exists a u for all x in the safe set, then, for instance, what can happen is that your system will exit the safe set. And this is the key concern that we have and we're trying to solve. So more formally, given some dynamics and a safe set with some bounded control inputs, we're trying to construct a safe set C star subset of S and find a set of control actions K ICCBF of X, which guarantee the forward invariance of C star. Now, a number of previous works have tried to tackle this problem, and I refer you to these papers and my paper for a closer summary of what they've developed. Here's an example. Suppose the adaptive cruise control problem where you're controlling the blue car with some acceleration u, with respect to a distance from this red car, which is traveling at a constant speed v naught. We can write down the dynamics of the system in a control affine form. And suppose we bound the control acceleration of the blue vehicle by 0.25 g's. We can say that the system is safe if d is greater than 1.8 v, as was done in Ames's Perversion paper 2019. We can draw the system in a state space diagram. Here we've got the speed of the vehicle in x2, and x1 is the distance between the cars. The blue region here defines the entire safe set. However, if we think about this problem carefully, we can see that there is a region over here where you are very close to the car but traveling very quickly, where you do not have enough control acceleration to be able to stay safe. If you enter this region over here, you are bound to exit the safe set. Now, this particular region is quite easy to determine because this is a single input system, relatively simple system. However, in general, this is quite a difficult problem to find. We cannot find this boundary over here easily. You would have to use a method, for instance, reachability or Hamilton-Jacobi methods to be able to find that region. So what we're looking for is we're looking for some inner safe set. So this is C star over here, which is guaranteed to be inside of this region over here, without knowing what this region is explicitly. And I'll show you for our particular construction, we get this sort of safe set C star. Let's think about this problem a little bit more abstractly, so that we can think about how we can solve the problem. So we have the system over here. There's a region of the state space over here where if you enter this region, you would be exiting. Now, we don't know where this blue boundary is, so I'm just going to hide it. And now what we can do is we can test the regions on this boundary and see whether or not the boundary is safe. So this dashed region of the boundary is a set of states where if you arrived at that boundary, you do not have enough control authority to stay inside the boundary. And so you would be exiting, you don't have enough control authority to stay inside the safe set. And therefore, if you arrived at this state, you would be exiting from the safe set. The region in solid over here is those where you do have enough control authority to stay at least locally within the safe set. And so now we're trying to find a inner safe set. Now, the way I'm going to do this is by introducing a new function b of x. We're going to define b of x as the infimum over all possible control actions of h dot plus alpha h for some user-specified alpha. This allows us to define a set C. Notice that because we've taken the infimum over all control actions, this function b of x only depends on the state that you're in. And the specific control policy that you use is no longer necessary. It allows us to define a region, for instance, C over here, and we're going to show two useful properties of this function b. First of all, suppose you were on some state in the boundary of S but one where there does not exist a safe control input. So if you arrive at this state, you are guaranteed to exit. We can show through a series of very simple algebra that in this case, X is no longer in this set C for any user-specified class A function alpha. So this allows us to see that B is a way to trim away regions of the boundary that are unsafe. The second useful property is if you consider some point X, which is on the boundary of S, but it's also inside the set C. If you do the similar set of algebra over here, you can see that since H is 0, this whole term disappears. And now you can see that for all U that are safe, that are possible, H dot is possible. And what that means is that if you do have a controller that can keep you inside the set C, then regardless of what then with that controller, the set S intersecting C is going to remain safe, is going to remain forward invariant. And so now the whole problem has shifted from requiring S to be forward invariant to requiring C to be forward invariant. And in some cases, it's analytically possible to show that C is forward invariant, or you might find a region of C that is not forward invariant, or at least a region of C for which you cannot keep it inside C. And so what do? You can repeat these steps. And so by repeating these steps, you can construct a new set which will remain safe. Let's formalize this idea a little bit more in the next slide over here. So let's say you're given some safe set S. We define a function B0 as h of x. Next, we construct a new set C1, which is the set where B0 dot plus alpha B0 is positive. That defines B1. And you continue doing this a few more times. Just to clarify, so what B1 looks like is you can expand B0 dot into LFB0 plus LGB0 using the Lie derivatives. And notice that B1 is not dependent on U itself. Now, if you continue the steps a few more times, you can arrive at Bn, where Bn is defined in a very similar fashion. Finally, you define C star as the intersection of each of these sets, so that becomes this yellow region right here. And now you can define a ICCPF. So the definition of the ICCPF is that if there exists a class K function alpha n, such that for all x in this yellow region, you can show that Bn dot plus alpha Bn is positive, then B of n is a ICCPF. The key property of ICCPFs that is useful is given in this theorem, which is the main result of the paper. If B of n is an ICCPF, then any Lipschitz continuous controller such that Bn dot plus alpha Bn is positive renders the set C star forward invariant. And because by construction C star is a subset of S, we know that we have found an inner safe set, and we've found a set of safe control policies such that we can remain inside this inner safe set. Let's think about how this applies to the adaptive cruise control problem. If we apply the standard CBF QP, which is from this paper, but we clip it to lie within the range of acceptable control inputs, you will notice that by clipping the control action, we enter a region that is unsafe. And so because of the fact that H is not a valid CBF due to input constraints, we can see that this standard approach would fail for the system. You would either have to find another alpha, or you would have to run a few more simulations to determine whether or not you can maintain safety. Now, how do we use ICCBFs? We start with this h of x. We can define B1 as a new set. For instance, let's say arbitrarily we chose 0 equals 4R. That gives us a new set C1, but you can notice that there's a region of the boundary that still is unsafe. So you repeat the steps. You define a B2. In this case, let's say we took alpha 1 equals 7 times root R, and you can show that this is the new region C2. Along this region C2, you notice that this boundary is entirely solid, indicating that every point on this boundary can be maintained safe. And because of that, we can define C star, which is the intersection of all of these states, as the region which can be maintained safely. To maintain safety on this region, we just define a set of safe control actions, which is B2 dot plus alpha B2 is greater than 0. In this case, I chose alpha 2 to be equal to 2R. If we show on the same plot what has happened, you can see that the system starts to decelerate earlier. In fact, it starts to brake earlier, and it doesn't need as much braking authority as the maximum braking that is allowed. And because of this, the system remains safe throughout the time horizon that we can see. In this way, ICCBF has been used to be able to convert a safety condition into an inner safe set to be able to, that can be implemented directly on hardware. Now, finally, I'll show you a simulation result for a more complicated scenario. The scenario is that of docking. So imagine we have a target spacecraft, in this case, for instance, the ISS, that is in orbit around the Earth. And we have a chaser spacecraft that's trying to dock with it. We're going to be describing things in the local frame of reference. And here we have the chaser trying to enter the target and dock with it. The target itself is spinning at a constant rate. And I won't be assuming the standard linearized dynamics, I'll be using the full non-linear dynamics. Because we're controlling the acceleration of this vehicle, the dynamics, the safety condition is of relative degree 2. In particular, the safety condition is that we must lie within this line of sight cone of the target. And we're going to be introducing a CLF to be able to track ourselves towards this target point at the docking port. Here's a video of how this works. So here we've seen the target that we're trying to dock with. Over here is the chaser that is going to be trying to dock. And the purple region here defines the line of sight cone. So if we play the animation, you can see it starts inside, and as the simulation progresses, it will stay safe and enter and dock with the target. So in conclusion, I've introduced a method to construct ICCBS. I've shown some simulation results, and I refer you to the paper for full details on this. As far as remarks go, we can also show that this method of ICCBS are a generalization of higher order CBS that were introduced by Excel in 2019. In particular, some of the terms that appear in our derivation disappear if you consider a high relative degree system. I also introduced the concept of simple ICCBS in the paper, which introduces conditions upon which you do not need any safety critical controllers. Because of the boundedness of your safe set of your control actions, you can show that your safe set is naturally bounded if you satisfy the conditions of ICCBS. In the future, we hope to investigate things like noise and robustness, and also the verification of the conditions for ICCBS. In particular, we showed results that set sufficient conditions on whether if BFN satisfies certain conditions, then BFN is an ICCBF. To verify that, at the moment, we've been doing that numerically, but I would like to see further results on how we can verify that a system possesses the ICCBF. Thank you very much.